In this demo, what we want to show is how to use the GIS capabilities through CyberWater or in CyberWater, and also how to use these connections to GIS to run and execute some models, sorry, like the DSVM. So those are the two parts we want to show. And let's just start with this. To execute each one of the GIS, any of the GIS tasks, we can use this GIS run module agent. And what sorry, I have this Zoom in front of me. Okay, what we do with this GIS run module agent is give the name of the execution we want to do in GrassGIS, the task that GrassGIS uses, and the parameters. And it has a way to control the execution with a ready flag, like this one called ready to start flag. So if we want to begin the execution with this one, we have to create our ready to start flag as true. And what we're first gonna do is gonna upload a DEM map inside GrassGIS. And for that, we use these tasks called R in text. And every single one of our GIS modules require this GRASS engine, or everything that uses GRASS requires this GRASS engine module. And what this guy is GIS engine. And what this guy does is create a connection between CyberWater and GRASS, so that the execution of the modules doesn't create multiple paths and we have just one clear connection to GrassGIS. It is also clear for the user to know which parts of your workflow are connected and use GIS features. So you just go ahead and connect this to the GRASS engine. And the only thing we need to do is give the command name, which is our in text. And the second thing is the parameters of that function. So the user will need to know, the only thing the user needs to know is which arguments each one of the function of GRASS have. And for this example, I have this R in text that has the output name of the map inside GRASS, the path of the DM map, the coordinates that bound the map, and these are two flags that are override the map in GRASS if it already exists, error, and keep the console quiet. So each one of the GrassGIS functions have this kind of sequence, and I have the sequence for another of the functions we have to create the watershed based on a DM map. So we just copy and paste this, and they have to be separated by a semicolon. So just plug it here, and if you can execute this, and what this does is just puts the map inside GrassGIS. That's all we need. So what we're gonna do is gonna repeat the use of the same module for two more tasks. So this one, what it does is focuses the GrassGIS engine in the area where this map is located. And to control the sequence of the workflow, what we do is just plug this into the ready to start and connect this to the GrassGIS engine that we have here. This our watershed function, what it does is creates a drainage direction map and a stream map and an accumulation map. And the drainage direction map is the one that is used to find what is the watershed that we have in the DM map or any of the watersheds. What we need to give is the coordinates of the output, and they're provided as one of the parameters here. These are the coordinates of the output. So that's all we need to give. I think we need to connect this GIS engine here. And what we want to do is to visualize the maps that we have created. So let's start just visualizing first the DM map. And these are, again, the GIS raw module agent, the same thing again. But here we're using a module to output the DM map as text, so CyberWater can read it. And we connect this ready to start, and we connect the GIS engine that is required for each one of them. This is the directory to static data set that we actually talked about in the first demo. And this is the show data set module that I mentioned that I wanted to show this last one. What this does is allows you to see each one of the data set individual maps in individual cells in a spreadsheet. So let's see. Okay, so this is the spreadsheet that shows us the maps. And this is the first DEM map that is, what we did is just put it into GRASS. We did the operations there, but what we did later was just export it and being read by CyberWater. But what we want to do is being able to read all the other maps that are created during this execution. Just go ahead and paste them. I have previously prepared this. These are the same procedures I did for the DEM, but for each one of the other maps, the drainage map, the streams map, the accumulation map, and the watershed map that is created in this water outlet. The only thing we need to do is just plug the ready flag for the correct module. So because we know this one creates the drainage map, the stream map, and the accumulation map, then we connect this one in these 3 columns. But this one has to be connected to the last one because this one is the one that creates it. And everything else, as before, we have to connect everything to the GIS engine because all the modules require it. And also, this load map requires a space range because this is the one that loads the map to the actual CyberWater logic. So we need to connect this space range to each one of them so he knows where to put them in the space. I think that's it. So we'll just execute this again, and this would rewrite all the maps in the spreadsheet. So this is the repeated DM map. This is the drainage direction map. This is the streams map, like identified in the DM, the watershed, and the streams of the map. And this concludes this part of the demo. And the other section that we want to show is how we use the GIS engine to perform 2 main tasks that are actually done by GIS. And one of them is find the exact output where a river might be located. This box only requires an approximate area of the basin and an approximate estimation of the output coordinates. And these are 2 very easy to find data that you can get in the USGS, for example. If you want to search for that, it will give you an estimate of the area, and also the location of the station, which may or may not be exactly in the river. But for the purposes of identifying the watershed, we need an exact point of where to look for that watershed. So we need to find the exact coordinate output. So that's why this module was created. And the second one is the actual DSVM agent. So the DSVM agent creates the drainage network of the rivers and makes the routing on itself. So that's why we need to provide the GIS engine into the DSVM agent. And because this is a high resolution model, we are doing the Indiantown Run Basin, which is very, very small, has 14 square kilometers. It's in the middle of PA, and we're executing 1 full year of hourly simulation. And because it's hourly simulation, then we use these NDLS agents to like download the information. And we compare the results with USGS information, but because the USGS sometimes gives information that is has more time resolution that we require hourly, and this USGS is giving us information half hourly. So we need to transform that using the time rescale module, and this is their final result. So all the results we have shown so far up to this demo are non-calibrated. What we do is we just use default values for the execution of the parameters in the correct format. The user, if you want to do calibration, the user can go right now to the files that are already created and modify them until you obtain something satisfactory. If you execute this workflow again, what this DHSVM would do is reread the files, the new files you have modified, and use them instead of creating new parameter files for this execution. In the future, what we plan to do is to add a specific calibrator into the CyberWater, but that's what the user has to do right now. If there's any questions, I haven't seen the chat.